Today's lecture is going to be about prediction error method. After we have learned the topic about the linear least square, about instrument variable method, you will see that those frameworks can be applied for linear model where the error term of the regression model can be written as if the error term is linear in the model parameter. Okay, so when that assumption no longer holds, we need to find another framework, and prediction error method is one of them. Okay, so today the lecture of PEM, okay, is going to discuss about first the description of the method. Okay, and then we will talk about the topic of optimal prediction. So when you have the measurement y, okay, we use notation y hat as the prediction or the estimate of y. Okay, so what is the best estimate of y? That's optimal sense. We're gonna define the optimality, and we're gonna actually characterize the form of the predictor for linear model. Okay, the concept of PEM can have one example as a Kalman filter. Kalman filter is a linear estimator that is derived based on state space equation. Okay, and we'll also talk about the statistical results, statistical property of the PEM estimate, and we'll show you some numerical results. I think this video clip would cover only the two topics, all right, the definitions and the optimal predictor. Okay, so the PEM start from the definition of the error that is called prediction error E. It is the actual measurement YT minus its prediction. Okay, so if we take a look at the form of the notation, everything closely, I use E as a function of T, which is time, and a function of parameter theta. So this theta is a model parameter. It's a function of theta because look at this term y hat. If you use the notation y hat of t, that means this is a prediction of y at time t with the condition notation given. It means that this y hat can be computed based on the information up to time t minus 1, up to, all right? It can use the information of y, at time 0, 1, ... all the past data up to time t minus 1. That's why it's called prediction y hat. You want to predict, because at this stage you only know the information up to time t minus 1, but you want to predict the next step of y. Okay, this notation also has a semicolon and theta. That means your y hat, all right, is going to be an output of your model. This is your model, or can call it the predictor. It's something that you construct, all right? It's going to be a mathematical model. The input of y hat is, of course, is going to be the information of u and y, the measurements, but it's going to be information up to time t minus 1. All right. So in this model, in this predictor form, it will have some parameters. So that's why your y hat is a function of theta, and the error term, of course, is a function of theta. Right. So the predictor term, we say that the general form is the following. The general form requires two inputs. Now, don't be confused with the term input of system, all right? So you have input and output, right? Input U and output Y. This is your physical system, your real system. You want to estimate G, okay? Now, in this lecture, we're talking about, as I said, we construct something. This is called a predictor, okay? This predictor, the output of this predictor is to predict, all right? is to predict the y hat of time t, but we require to use two types of input of the predictor, that is y and u, all right? And of course, we use these two inputs that apply to the two filters or transfer function L and M. Okay, L and M, it has a requirement, very important requirement. It says that L and M must contain one PL delay. In this notation, let me remind you that L is a function of what? It's a function of delay operator. Q inverse is called delay operator or lag operator. For example, if L is given by 1 plus 2 Q inverse plus 3Q minus 2, okay? If you apply this filter on Y, that gives you YT plus 2YT minus 1, all right? One lag step plus 3YT minus 2. Okay, that's the notation of the delay operator. Okay, so when we say that L and M must contain one PL delay, what it means is that L when the input argument is 0 must be 0. With this example, L0 is what? L0 is 1. All right, L0 is 1. So it means that, of course, L0YT is going to be YT. This L doesn't contain PL delay. All right, if L contains contain one PL delay, the output of L must contain only past information of Y. Okay, the L that satisfies one PL delay, it means that you cannot have the constant term here. You must start with Q inverse, okay, and so on. Okay, is this point clear? Is this one clear, Toto?
Yes, it is clear.
Okay, and of course the motivation that L and M must contain one PL delay, so that it means that the input of Y hat, all right, can contain only the input information up to time t minus 1, as required by the definition of the predictor. All right, when you predict something, all right, at time t minus 1, you want to predict the value at time t. Okay, you cannot use information of time t, because at time t you already have the measurement of yt. Why would you bother predicting yt then? You cannot use the information from the future. That's not possible, right? That's not realistic. So this is the definition and important requirement of general linear predictor. The method of PEM involves several elements. Let me break down one by one for you. When you choose this method, okay, the first thing is that regardless of the parameterization of your ground truth physical model, okay, so I would use a physical model. Physical system would be a better word. You have a physical system. I can also use the term ground truth. All right. This is like the real system that you never know. You never know its exact mathematical description. The ground truth relationship can be non-linear, can be linear, you don't know, right? But whenever you perform system identification, you must start with a model structure. You must start with the form of the model you're going to use, all right? So this gonna have some certain structure. You believe that this model is the actual one. All right. You believe that this model structure, for example, you believe you're using ARMA model. You believe that ARMA model is the structure of your physical system. Okay. And then you parameterize it into general form. Okay, I will give you the description again. The general form of system is y equals gu plus h times error. Okay, this is error e or nu. Okay, and next you start building this. Okay, and then you're gonna pick the choice of the predictor. You're gonna pick the choice of L and M that satisfy this one PL delay condition. Okay, and then next, based on that predictor form, okay, you can write. So these L and M will contain some parameter theta, and then you will, of course, you can construct y hat t given t minus 1, and then you will get error term, right? And then how can you pick theta? How can you pick theta? That based on the form of that predictor, the best theta should be selected so that some criterion of your parameter is fulfilled. That is called the choice of criterion. Okay, that f is a function of error. Okay, you measure the size of error in some sense, like whether it's big or small, and you're gonna pick theta that this thing is minimized. Okay, the term that we see before in the least square is that, okay, you pick beta so that the error square is minimized. That is a form of criterion function. Okay. So to perform the prediction error method, it contains 3 main procedures. All right, but we will discuss that at the second procedure. When you pick the choices of the predictor, let's pick the one that has optimality condition, is the one that has optimal mean square. Okay, the choice of L and M can be many. Okay, I repeat again, but there's going to be one choice that optimal. It's optimal in the sense that it gives you the minimum mean square error. Okay. So in the next slide, let me discuss about the choice of criterion a little bit. All right, this is called the loss function. Suppose you have the error term. Okay, and for SISO, the error will be a scalar. For MIMO, the error would be vector. Okay. Of course, the error would have the same size as y, right? So y, if y is the vector rp, the error would be a vector of rp. Okay. Now of course, how can you determine the magnitude of E in some sense? When E is a vector, we perform the sample covariance. Okay, you perform outer product of E. You take the sum from all the time samples and take the average, right, divided by n. This is a sample covariance matrix. What do you know about its property? Outer product, when you see outer product of two vectors, okay, is it positive semi-definite? Napat? Napat?
Outer product.
This is outer product of two vectors. Outer product and inner product are not the same thing. This is inner product. This is outer product. Inner product is scalar. Outer product is
Matrix.
Yes, if X is in Rn, X transpose is a matrix of size
N by N.
N by N. Okay, I'm asking, what do you know about the positiveness of outer product XX transpose? Is it positive? Is it positive semi-definite? Is it indefinite?
I think it's positive semi-definite.
Positive semi-definite, all right? It's never positive definite. This is a rank one matrix. Why is it rank 1? Because this matrix has only one non-zero eigenvalue. Okay, so you know that this guy outer product of of a vector, positive semi-definite. So this guy is always positive semi-definite. If you have the sum of many positive semi-definite, of course your sample covariance is positive semi-definite. If n is large, okay, if n is large and if ET are independent, it's possible that the sum of many terms can produce positive definite of R. Okay. Now, these are, all right, these R is a matrix. It's a matrix of P by P, let's say. Your Y is a vector of RP. Okay, and if you assign some function of the matrix R, F is going to be a function of, okay, what do you know about R? Let me go back a little bit. Is it positive semi-definite? So is it symmetric? Kanatat?
I think yes.
Yes, is symmetric as well. So if I define some function f that map from symmetric matrices to a scalar, okay, this is called a loss function. All right, and at this point, you have created a sample covariance matrix, and the meaning. Okay, let me break down. Suppose your E has at time t, all right, it has a E1, E2, EP. That ER is the error of the ith component of Y. Remember that your Y can be MIMO, right? So you have Y1 dot YP. Okay. What is okay, ET transpose? Can you expand this matrix for me, Totok? Can you give me the 1 element?
It is E1 times E1 in the diagonal E2 times E2 until EP
Yes.
times EP. Yeah.
Totok, can you give me the IJ element?
It is
Rooster from your house?
sorry.
Chicken. No, it's rooster
yeah.
in the morning.
Yeah, because I live in village. It is E1 times E2.
No, just IJ. Just go directly to on IJ entry. IJ.
EI times EJ plus 1.
Y plus 1. E1 dot EP multiply with its outer product. If I ask for IJ entry, you look at the ith row.
EI times EJ.
Yes, EI times EJ. Okay. All right. This metric we know that it's guaranteed to be positive semi-definite, right? And then, of course, what's the meaning of the covariance matrix? What does it tell you, Ping Lim?
Covariance, so the relation of these two. This, yeah.
It's a covariance of E, right? Okay, what does it tell you? Give me the meaning of the diagonal element. What does it tell you? If the, of course, for example, if the 2 element is big, what does it mean?
that it has relation. It has like I don't. I'm not sure, Chan. Sorry, I don't know how to say.
Okay, Sitipak. If the two element is big, what does it mean? Is big relative to other elements in the diagonal?
It means E2 has big variance.
As bigger variance, right, in relative to other components. All right. So that's why, as I said, the sample covariance R can give you a sense of, you know, how well you can perform the prediction. Because if your predictor is well designed, it has a better performance. It means that the covariance matrix should be big or small in the matrix sense. Kanatat.
It is big. But could you repeat it?
Repeat the question. Okay, you're designing the predictor. You're gonna perform, like, you're gonna find a way to construct y hat. Okay, your y hat will give you the error. All right. So I say, of course, a good predictor should be the one that yield a small error. All right. But we use this error to compute the covariance, the sample covariance matrix. So in the matrix sense, so a favorable predictor should be the one that correspond to big or small sample covariance matrix.
Small one.
Small one, you want it to be small, okay? But the thing is, it's a matrix. That's why you need a loss function. You need a metric. This is the term metrics. Metric is something that you determine quantitative measure of something. In this sense, you want to measure how small a matrix R would be, how small, how big. That's why you come up with a choice of loss function. So that choice of loss function should give you this sense. It should have the property that this f is monotonically increasing. Okay, this loss function maps from a matrix to a real number. Okay. So what do we mean by monotonically increasing? It means that you have a matrix X that is positive definite. You have a perturbation delta X that is also non-negative. Okay, when you perturb X by delta X, it would yield a loss function value that is always bigger than Fx. Does it make sense? Because I mean, from these two properties, X plus delta X and X, can you compare these two matrices in a matrix sense? Napat? Compare. Bigger or smaller?
No, we cannot.
Or we cannot compare. Given that X is positive definite, delta X is non-negative, can you compare? Oh?
Yes.
What is it, Toto?
Always bigger or equal.
Is bigger, right? I mean, X is a matrix. Remember the definition of like A bigger than B? We say A bigger than B if and only if, Toto.
Yes.
When we compare two matrices in a matrix sense, matrix A is bigger than B if and only if. What is the definition? City Park.
Bigger.
No, I recall back to the definition of how you can compare two matrices.
A minus
B. Yes, A minus B.
is positive semi-definite.
Yes, okay. If the difference of two matrices is positive semi-definite, and obviously you know that X plus delta X minus X is of course delta X, right? And which means I specify that your perturbation must be non-negative. So it means that when you compare x plus delta x and x, that is always greater, equal or greater than x. All right. So what am I doing now? I try to say that your x is here, this is your x plus delta x, all right? X plus delta x is always bigger than x. Your function f must be monotonically increasing. In this sense, this is your fx, right? From the function of real value that you know before, fx is x squared. Is it monotonically increasing on r, on non-negative r? Sitipak? Give me some example of non-negative. Give me some example of monotone. Oh, can I just say that the function f is always increasing? Example.
F equal x.
Yes. What else? Can you give me some more?
F equal exponential x.
Exponential x, very good. More, can you give more?
X to the third, x cubed. X to the third.
But yes, that's of course, that is fine as well. What about the log function? Is it monotonically increasing? What about log?
Log base a when a more than 1.
Oh, you don't forget about the log base. We always use natural log, okay, in this class.
Yes, it's monotonically increasing.
Okay, function log, okay. All right, these are examples. So we kind of, this is the same concept. We try to find a loss function, but it's a function of matrices, all right, mapped to a real number that has that property. Why do we care about this property? Because so that when we use f to measure the size of sample covariance matrix, then we have a sense that, oh, if the covariance matrix is getting bigger and bigger, this function value is bigger. Okay, and then what we're gonna do is we're gonna select theta to minimize this f function. All right, that's the whole point. So let me give you some example of the loss function. The typical one, okay. The first one is the trace is the trace function. Suppose you have the matrix W that is positive, definite, okay. This trace function fulfill the increasing property f. So what I'm doing now, I'm gonna verify that f plus delta x is bigger than fx. Okay, so because I'm just gonna start with the of course with the definition. F x plus delta x is gonna be trace of w x plus delta x, and because of the trace function. Trace function has a linear property. Trace of a plus b is ping.
Trace A plus trace B.
Trace a plus trace b. That's why you can expand, all right? And now, trace of wx is actually fx, right? Now you look at the green term. If you can conclude that the green term is non-negative, then you have proved this increasing property, right? So now let's take a look at the green term. Is the green term always non-negative? Now we use the trace property again, that this looks like the trace of the product, all right? It's a product of two terms that are non-negative. W is positive definite, delta X is positive semi-definite. We have this nice property about the trace that if a matrix, if A and B are two positive semi-definite matrices, trace of the product A is always non-negative. Okay, so let me sketch you some quick proof. If A is positive definite, What do you know about positive definite A? Does it have a factor? Napat?
Again, please.
Okay, one important about non-negative matrix. All right, if A is positive, that important property is about having a factor. Okay, what is it? That A can always be factorized as
Sorry,
like
I don't.
4 can be always factorized as 2 times 2. 4 can be factorized as -2 times -2. We involve with quadratic factor all the time. If A is positive definite, A can be factorized as
A to the power of 1/2.
square root, right?
Yes.
Or you can use other term. It can be factor as L transpose.
Yes.
Or I mean there can be like many ways to factorize, but the thing is, this is a square root. This is kind of this is called a factor. Some people call it a square root as well. Okay, for example, Cholesky factorization, LDL factorization. Okay, so let me use this term. If A is positive semi-definite, A has a quadratic factor. It has a quadratic form always. So you put L transpose in here, and then B. Okay, but then because of the circular property of the trace, circular property, it says that trace ABC is circular property. Sitipak, do you know what that is?
Trace CAB.
Trace CAB. So I'm going to move around. Trace LL transpose B is going to be, can Sitipak? Can you
BL
apply?
transpose. L transpose.
Can you move L instead?
Or L transpose BL.
L transpose BL. All right. I do it this way so that I can recognize that the matrix I'm going to take the trace now is a form of L transpose BL. That is certainly, what can you conclude about the positiveness of L transpose BL? Toto? We start with assumption that both A and B are positive semi-definite, right? And now we take a look at this matrix L transpose BL. Toto?
Always positive.
Positive semi-definite, right? Because again, this is quadratic form. L transpose L, quadratic form that is parameterized by B, but B is positive semi-definite. So the whole thing must be positive semi-definite. All right, is it clear?
Yes.
All right, if you're taking the trace of positive semi-definite, what do you know about the results of the trace? Kanatat? You have positive semi-definite matrix. You take the trace, which is the sum along the diagonal.
Yes, so it's have to be possible. Positive.
The trace has to be non-negative, right? Because the trace is a sum along the diagonal. Whenever a matrix is positive semi-definite, necessary condition is that diagonal terms must be non-negative. Or you can think of the trace is a sum of eigenvalues, right? So if a matrix is positive semi-definite, all the eigenvalues must be non-negative. So the sum of all eigenvalues must be non-negative. You can conclude from that point of view also. All right. Okay, are we done now? So this is a very important property. You can apply to other results as well. two non-negative matrices, you take the product and the trace, and then the trace is always non-negative, which means go back to the green term that we just explored. The green terms here must be always non-negative. So that's why we conclude that f of x plus delta x is always bigger than fx. The linear function in x, the trace of wx is linear in x, right? Is a increasing function, monotonically increasing function. But it is only has increasing property when w is non-negative. Let me just explain that. You know, this is a function, again, this is a function that maps from matrices to scalar. When everything reduces to a scalar case, it is simply a linear system. I mean, if x is real, okay? If everything, the matrix x reduces to scalar, this is a form of linear function. And you know that this is a linear function, fx equals wx. So it has only increasing property when the slope w is positive, right? Because if the slope is negative, this is not increasing function. So that's why the condition that the matrix w has to be non-negative is required. All right. Okay. Now we take a look at the second one. All right. Okay. The second property, the second choice of the loss function is determinant of the matrix X. I also would like to mention first that when you have a matrix, a positive semi-definite, all right, when you have a matrix X that is positive, okay, never mind. We just, I think it's better to go directly to the mathematical property. Okay, now I would like to verify that this function f is is monotonically increasing. Okay, so now I'm gonna start with writing down fx plus delta x equals det of x plus delta x minus. Okay, now I'm gonna take the minus. Minus determinant of x. Okay. Now I'm going to use the property that the matrix X here is positive semi-definite, right? So it has a square root. So when it has a square root, I can write X as the X square root times X square root. But I can also split it. I can also write x square root, like I multiply and then I cancel, right? Like I multiply with the inverse and then the square root. This is the same thing. And then what I do is that I factor out the common factor in the to the front and to the back, and then I have this factor, common factor, and this common factor, the square root of x. Everyone follow? Okay.
Yes.
Yeah, yeah.
Yes. Okay. So now you have the product of determinant of the product of three terms. What do you know about the det A times B times C? Kanatat?
It can be split to that A, that B, and that C.
Det A, det B, and det C. Okay. So now look at the first and the third one. What is determinant of x square root times det of x square root? What is it? Total.
Equal to determinant of x.
So it goes to the determinant of x, all right? So that's why what we have here is determinant, okay? Let me just sketch here. So it's the determinant of x, determinant of the long term, like this messy term, and minus determinant of x. Okay, and now you can just, what you do is that you find that determinant of x is a common factor. Okay, everyone follow? This is a common factor times determinant of this long term minus 1 from here. Okay, and now we're gonna notify that we're gonna notice that this long messy term here, it has the form of determinant of I plus something. I call it a triangular symbol here. What do you know? Okay, and maybe I call it I plus A, where the matrix A is this one. First, you apply this property that, what do you know about the determinant of B? What is the relationship with the eigenvalue of B? Ping. Relationship between determinant of matrix and eigenvalues of the matrix. Ping. Ping, not here. Kanatat.
This one could be
What is that? Determinant and eigenvalue, what is the relationship?
I mean,
Okay. Sitipak.
Is the multiply of eigenvalue in B.
Is a product, right? Product of eigenvalue of B. Okay, that's one thing. Give me another property. What do you know about det of I plus A, Napat? Is there a relationship? Also, not that yet. What is the relationship? I mean, if you explore the eigenvalues of A plus I, like you perturb A by identity matrix, what would you know about the eigenvalues? Is it related to the eigenvalues of A? If it does, how? Napat.
I can't remember.
Total?
I don't know either.
Sitipak?
1 plus eigenvalue of A.
1 plus eigenvalues of A. Okay, you can prove real quick. Go back and check it out. If you perturb A by I, Sitipak, what if I have a constant alpha I? Okay, what would it be?
Alpha to the n. N. Or n alpha.
No, without the factor
just
n.
alpha.
Okay, just alpha plus lambda A. Okay. All right, this is a important result. So, again, let me go back to the I. Okay, that's going to be 1. Okay, so then from the first property, what do I know about determinant of I plus A? Can you apply these two properties? You know that the determinant is a product of eigenvalue, but the eigenvalue of I plus A is actually shifted by 1. Okay. So this when will be total when you apply 1 and 2, it's gonna be product สมทบ product over k the product of สมทบ is going to be a product of lambda of I plus a, right?
Yeah.
But lambda of I plus a is Napat
is 1 plus lambda of
is 1 plus lambda of a. Okay? Now that's why we end up the yellow term reduce, not reduce, I mean we end up with having the yellow term. Okay? The determinant of the matrix in the yellow area, okay, is the product of 1 plus eigenvalues of A. Okay. And then what do we know about, okay, let's take a look at the term in the bracket closely. Okay, you have -1 here. Because this matrix A, okay, can you now can you see the property of the matrix A? Can we say that A is non-negative? Napat?
yes.
Why? Okay, Napat, why?
Because delta x is positive semi-definite.
Okay, the delta x is non-negative, right? Whenever you put a factor, you know, in the front and is transposed in the back, it doesn't change the positiveness. I mean, we always have this property all the time, A positive, right? When you transform A in this sense, like B can be any rectangular matrix, right? This is called congruent transformation. Okay. Congruent transformation, this is a new metric, right? New metric C. It is, it preserves the positiveness of A, which means it says that C is still positive definite, positive semi-definite. Okay. So the matrix A is positive semi-definite. So what do you know about the eigenvalue of A? Ping?
It's positive.
It is always non-negative, right? Okay, if you have, now look at the term, if you have 1 plus something non-negative, okay, so you have the product, so you have the product of many terms, right? 1 plus something non-negative. Can you compare this product with 1? Totok?
Always bigger or equal to 1.
Okay, right, product of many terms, and those terms, each of those terms are 1 plus something non-negative. Of course, the product of these terms always bigger than 1, all right? So that's why this term is always non-negative, and determinant of x is also non-negative, right? Because that's the assumption that your x is non-negative. That's why we have proved that this f has a monotonically increasing property. All right, the determinant function is increasing. And one important property is also, I forgot to mention, is that for this loss function, okay, it requires some this important property as well, that the function value of the perturbed x equals to the fx only if and only if that perturbation must be 0. Okay, so you want to have a loss function that, you know, the function values can only be equal in one situation. One possible situation is that perturbation is 0 itself. All right. So basically, if this is your x, okay, you don't want a loss function that looks like this, which means there could be 2x, right? 2 possible values of x that return the same value of loss function. You don't want this case to happen, and that's why you require this assumption. This assumption is satisfied for both examples. Can you please check? Okay. All right. I think it's been 1 hour already. I would like to break the video so this video clip explain the overview concept of PEM. It says that it has 3 procedures. Okay, you have to define the model structure, pick a choice of model, pick a choice of the predictor, and pick a choice of the criterion. We have spent the time on the discussion of the loss function. In the next video clip, I will discuss about the optimal form of your predictor.